This is Swarfcast. I'm Noah Graff. Stratasys was the first 3D printing company I visited at IMTS 2024. In the first part of this episode, I speak with Foster Ferguson, Director of Aerospace.
Yeah, Foster Ferguson. I'm the Senior Director for Aerospace and Defense at Stratasys. And my background is I spent 20 years in the Marine Corps. And so I've been at Stratasys for 5 years now. And we do a lot of work with a lot of big companies, and the Lockheeds, the Northrops, the Boeings of the world, and a lot of our defense customers as well. So that's our story.
And Tom Leach, commercial leader at Stratasys.
This is the H350. This is our SAF technology, our selective absorption fusion. And so what we're really targeting here is high or large volume production, so tens of thousands of parts. It's a high speed sintering technology, essentially laying a layer of powder, laying a binder, and then thermally binding that part together. And what you see here is a representation of the build volume. What you see is this is a Ford F-150 Roush Performance Raptor, and this is a mounting bracket that goes behind the grill that holds the camera in place. This is a production part in every Roush F-150 Ford Raptor that we're displaying. This is actually all put together, and we do this so you can have a representation of the build volume itself. So this is what that part is, and where we feel that this is a huge growth lever for Stratasys, because we are competing with injection molded volumes going into tens of thousands, where the more complex the part, the better it is for additive manufacturing, really solving manufacturing challenges of lowering the investment cost on tooling. So this is a really big opportunity for Stratasys, and this is the major direction which our company is going to be looking to grow in.
Can you define, dumb question, but can you define sintering? I've heard it a zillion times.
Yeah, it's a great question. So sintering is essentially fusing plastics together to make the final component, the final part. So we're applying mass amounts of heat, and we actually have really great thermal control with our system here, and that's actually a really good strength. That's why we can have up to 30% pack densities on this technology. And so it binds the plastics together and it sinters them. So I hope that answers your question in terms of what sintering is. So it's binding the material together. It's a plastic with a binder, and then with the heat, it binds it together. Does that make sense?
So sintering is binding?
Yes, binding, yes. Fusing, binding, exactly.
Cool.
Yeah.
So it's pretty cool. So this is where we get into the low volume production we talked about right now. So, I mean, Tom explained an automotive application here, a full, known production application that we use with, Roush is an aftermarket producer of Ford trucks, but you can see this also a lot in a lot of drone manufacturing as well. I mean, you start to get in, so drones are a very big and growing market, right? With not only defense but then commercial aerospace as well. So you're starting to see designers coming up with drones that are kind of consumable drones. It could be throwaway drones. We call them attritable drones, but this is a great application for it, right? And then you can just quickly crank out a bunch of drones to do things.
In multiple iterations. So when you're doing production with injection molding, if you have iterations on that mold, it's costly, it's expensive. You sometimes have to redo the mold completely, or you have to make iterations or change that mold. It's expensive. Here, you're not penalized for design freedom. So if you have a design flaw and you catch it 100, 200, 1,000 in, you don't have to change the tool. You can just quickly change the design. So it is extremely cost reductive for tooling applications and moving that cost down, and really for advancing your product. People can't make changes even though they find an engineering change too late. They can't invest in the new tooling. So this is a way for essentially smaller, people that don't have quite the investment behind them, they can get into the market at a much lower cost.
Interesting.
Not penalized, but optimized.
Yeah.
I never really thought of tooling as that big a deal. I mean, you just go to Sandvik and...
It's millions of dollars, billions of dollars. To retool an automotive facility, it's like 20... Yeah, and thinking of the molds and all of that, it's extremely expensive. Molds can be 10,000, they can be 100,000. And the lead times on those molds, 6-8 weeks, and then to do rework on those molds, I mean, you're paying in the tens of thousands of dollars to rework on those molds.
And this, you just buy the machine, get the material, and
you don't need a tool. You don't
push
need a
some
mold.
buttons.
Yeah, exactly. You throw it, upload the file, hit print, and you can also print 7 different parts at the same time, all at the same time.
Push the buttons. It's just as easy as working a camera.
Yeah.
7, probably easier than this. 7 different parts at the same time.
You can do 100 different parts.
Anything you want to do. It doesn't have to be the same part.
It doesn't have to be the same part. You can print any part. You can pack and dense any type of parts you want into a build area. I mean, and that's the creativity that you have and the ability, so that you can really you can do your main parts, but then you can plug in smaller parts around the main parts that you're really focused on, and really, I guess, go to production much faster.
So, you're talking about a drone. I mean, how much of a drone could be 3D printed?
Well, there's a fully, outside of the motor and the propellers, there's a, in this booth somewhere, we have a drone that's like 95% 3D printed. I would say, build. Yeah, and all in the same build.
But then you'd still have to get screws and wires and all that.
Sure. Yeah, potentially you could do the hardware, but you could design it so it snap fits and certain inserts where you don't need to do that. You can actually design the hardware if you want to. So if you think about this forward deployed, and I would say, let's just say Ukraine, what's going on over there, and you have the system, and you need to have a drone produced, potentially you could do everything but the motor in that production. So you could do screws, hardware, blades, the core, different components on there, have a deployable drone, and then put the motor in there, and then obviously you have to put the remote signal, but you could do 90-some% of that drone.
And you could do the motor too?
No, you can't do the motor. You cannot do the motor. The motor you have to order the motors from different sources. You cannot print the motor.
But you could print a motor, theoretically, on some kind of machine.
I don't know of a technology that can print the motor. I mean, theoretically, I don't know, but essentially if you printed with metal components and different aspects of it outside of the system, yeah, I'm sure you could, but I bet you there'd be a better lower cost option to do that traditionally. Like a motor, you have a few motors over here, in that cell over there. You'd probably have to just order those motors and then essentially build the drones there. So,
what are the parts that in the last year or two, like the biggest breakthroughs that you couldn't do the last IMTS that now you can do?
3300 already. So we've already talked about the 3300 not even being here 2 years ago, and so actually this technology was just coming to market a couple of years ago, right, Tom?
Yeah. So I would say, that's a really good question. It's a tough question. I think we've learned a lot of where it makes sense financially to do 3D printed SAF parts versus traditional manufacturing in those years. So we've looked at hundreds to thousands of parts, hundreds of thousands of applications, and we've really identified key markets and key applications that we're going to target as an organization where we can save customers money. So the technology's advanced. We've be able to add polypropylene. We have PA11 and PA12. So PA11 is what we launched with. PA11 is what we launched with, and just an example that it starts with this castor bean. It's not a food source, so it's a sustainable source. Goes to an oil, goes to a powder, and then it goes to a printed part. So this is just highlighting how this process is done. And then one of the advancements that we have is the material development. So we couldn't do polypropylene before, so one of the advancements is polypropylene. So polypropylene is the second most utilized plastic today out there in the world. And we partnered with a company called BASF, which I think is AM Forward now, branded AM Forward, and it's flexible. I mean, this is polypropylene, and be able to print polypropylene accurately, repeatable, and reliable. That's a major advancement for us as a technology. So if you think about where we can really target is people that are using polypropylene that have been limited to only traditional manufacturing sources. And it's because of the development with our high-speed sintering technology and our head technology and how we thermally manage the thermal heat and how we fuse the parts together or sinter the parts together, and with AM Forward and BASF's chemical development. So it's a great partnership and what we've done since the last time we've been here. So this is
very cool.
Yeah. So really, really great application. So
very cool. What's your favorite thing that you've ever seen made on 3D printers? Both of you.
Both of us. Oh gosh.
I know mine is.
You know what yours is?
So I'm not in the medical team, but I think the most coolest thing I've ever seen was a replica of a young girl's heart. The surgeon, it's an anatomical model, it's printed on our PolyJet technology. That surgeon that has never seen anything like it before, and there's risk if he goes in the first time and does it and he fails, that child dies. He was able to print that 40, 50 times and practice on that anatomical model using PolyJet, just through his provider, printing the replica of the girl's heart. Practice it, feeling confident in what he was going to do, and have better outcomes for that patient. And that girl is living today and survived. And it's because that they're able to PolyJet print that anatomical model with bone and tissue matrix, or tissue matrix replicating that heart, and that young girl is still alive. That's probably the coolest thing I've ever seen printed. Pretty cool.
That's amazing.
That's good. I'll give you the 1A on mine. And so I actually love that one too. It's because it's human life. It's like bringing it home, and it's a real impactful story. But we've got some other really cool prints as well, and I'll maybe pivot and talk about what we're doing in space on that. This is space, okay? So this material, right? We call this Antero, and this is what it's a PEC-based material, and we created this material in concert with Lockheed Martin. And in this specific material, what we've done is we've filled this with carbon nanotubes so that it does not produce static, right? So electrostatic dissipated material is really important. You don't want static in space, right? That's a bad thing. Could cause a reaction that you don't want to have.
Interesting.
So this
never really thought about that.
Yeah, this actual panel is something that is flying in the Orion spacecraft. There's about 300 parts on that spacecraft that are out there right now with this material. And so
it was made on Stratasys?
It's made on Stratasys printers. Yeah, that large F900 printer I showed you with the large build volume over there is the kind of stuff that we do with this. So that's what you would see here.
So they all seem to have this texture.
Yeah, a little bit of
that's intentional, or is that?
That's just the methodology of the print. I mean, it comes with the way that you orient the print, and what you're going to.
But it doesn't necessarily have to have that.
I mean, if you wanted to finish this and smooth it, if you didn't want that texture, you could certainly do that. But when you come right off the printer like this, it might have a little bit of those ridges.
I mean, when you were printing like the heart,
that's going to have a different technology. So it's going to be spraying a resin and curing it with a UV light. Whereas, and here's the heart.
Whoa!
And then this is, go ahead and grab that thing. It's pretty crazy.
So as you notice, the heart is actually different than the valves.
Give it a squeeze there. Feel it.
This is like what a heart feels like.
According to the technology, that's exactly what your heart feels like, Noah. So I don't want to stick my hand in your chest, do an Indiana Jones Temple of Doom thing. But yeah.
Good reference.
Yeah.
Part 2. As fun as the first interview was, this interview was what I was really looking forward to. I speak with Evan Hochstein and Allison Harbaugh, business managers for the Stratasys Medical Team.
Allison Harbaugh from the Stratasys Medical Team.
And
Evan Hochstein, also with the Stratasys Medical Team.
How did you get into printing body parts?
So I'll go first. I actually started off in high school. I joined a local robotics team, and that robotics team really inspired me to take on this challenge of engineering. And through engineering, I found I really had a love for impacting patients and individuals, people, making their lives better in unique ways. And 3D printing is truly a great way of doing that.
Yeah, and you, Allison?
So for myself, I actually started out in the manufacturing side of the world. So I used to work for 2 top orthopedic companies, then found the world of 3D printing and learned that there was a way to marry both loves of mine together. And so now we get a chance to support med device companies with use of 3D printers.
It's just so mind-boggling. Like, I can understand 3D printing some plastic, but cells and I find it a little strange that the same company that makes the technology to print plastic or metal will make, I know you guys don't focus on metal, but still, the company that would focus on making a plastic 3D printing thing would do the same thing on a live body part. It's a strange combination, isn't it?
So one way to look at it is they're all plastics. So we're taking very soft plastics that mimic tissue-like materials, all the way up to harder plastics, but that can mimic bone. And you can now take a patient's CT or MR data, convert it to a printable file, and now you can actually practice a surgery, you can test for new products, and you can create models that will mimic how a patient's anatomy is.
And to add to that, I think there's a fine line and delineation between what we talk about when we talk about manufacturing with plastics and creating anatomical models that look and feel realistic versus bioprinting and what we truly see what can go into a human body. When we look down the bioprinting side, the terminology changes to cells and nutrients and how do we appropriately deliver those nutrients to the cells so they grow and create an organ or a tissue that can be potentially in the future represented in the human body. It's not necessarily something that we can do today. Today what we're really looking at is more of the plastics that Allison is mentioning here with like this heart. So it feels realistic, it looks somewhat realistic, right? There's no blood flowing through it, but it's a model that we can go in, we can bring it into the operating room and have a surgeon practice a surgery or a clinician practice a surgery before they do it on a real live human being, lowering the risk and the chance of complications to that patient.
Yeah, right. And they were telling me before that you can actually like specify, oh, I want the heart of a 80-year-old or the heart of a girl or...
So we can change the stiffnesses of the material for your model. So what's great is within our software, it's a quick click of a button to be able to pick a certain type of anatomy, maybe a certain bone structure, certain tissue structures, certain tumors, maybe it's different organs like a kidney, and to be able to pick out what that should feel like.
And so this came from what, a person? You guys got one and then you, I don't know, put it into the machine and it imaged it, and that's how you did it?
So the model I have in my hand is really just a marketing model. So as someone who is in the medical field, they'll realize this is not exactly how every heart looks. It's very artistic. But to a patient, you can, as I said, take their CT or MRI data.
So this is not modeled after a specific person?
This one is not, but this is also allows us, because typically there's a lot of HIPAA issues of us bringing a patient's model to a show or an event like this. And so this is a way of just taking something that will mimic the design to show off what's capable.
Okay.
Yeah, something that we're doing on, we're looking at this from a macro scale, right? From a macro scale, it feels like a heart, it looks like a heart, but at the micro scale, really what we're doing is we're controlling what we call the voxel. And really the best way I have to describe a voxel is I call it building with Lego blocks, or maybe playing Minecraft, right? You're taking these 3D blocks, you're putting them together at a micro scale in order to simulate a real heart. So if you were to put this heart under a microscope, you're not just going to see one material that's called myocardium to represent that heart tissue, right? It's a combination of around 6 different materials that are actually generating and creating what we then print as a realistic feeling and looking heart. And that's how we can get realistic models like this eyeball. You think of prosthetic eyeballs, right? This I can take a scan of my eye, convert that to a 3D printable model, and then I have an exact replica of my eye that I could potentially use as an eye prosthetic in the future.
And this eyeball that you're holding up right now, this is from a dinosaur?
This is another artist representation, right? It's a perfect eyeball, for lack of a better term. It's created by an artist, usually in 3ds Max or Maya, and then it's 3D printed using our full range of colors on a J5 MediJet.
So this is just a joke that it was not like the thing that actually was, oh, let's make a dinosaur eyeball.
We could.
It's just a big ass eyeball.
Yeah, it's a big ass eyeball. It's a good way to put it. We even have an extra large version that I don't think we brought to this show with us.
So so the whole thing, it's just with the colors and everything. That's a representation, but we're not talking about representations here. We're talking about
So
the
this
actual...
is opening up to the world of people wanting to utilize our printers for prosthetics.
Sure.
So being able to create something that's truly realistic and being able to use that as another form of artistry rather than the standard way that prosthetics are made, which tends to take a couple of weeks, maybe even longer, where this could be printed in a day, and then shipped out to a patient.
This is the eye-catching model, for lack of a better term.
So, okay, so now on to you actually want to print, an arm of a person, like a real arm. How does that work?
So one thing that's truly exciting, so Stratasys about 5 years ago launched what we call our digital anatomy printer. So it was a very large format printer that's able to now mimic bone and tissue-like properties. As of this summer, we launched a new version, which is similar to the printer that you see here, which is our J5 digital anatomy printer, giving you a smaller footprint, easier to bring into most facilities, and you can really take any scan, any design, and be able to print that off inside your office facility.
One thing that's really important to us as we look at, utilizing this 3D technology is providing an end-to-end workflow. So Allison's done a great job of describing what we do from a hardware and a material standpoint, but software is still critical to how we are successful in this industry. So we talked a little bit about taking your CT scan, your MRI scan. We have strategic partnerships with companies like Axial 3D, Materialize, and Synopsys, where we've gone through and we've validated our technology to print these anatomical models with the FDA through 510K clearances.
I'm just keep trying to imagine, like, you've got cells and blood and...
So we do have some materials that are biocompatible, and customers would use them for something similar to this, though this is of a different material that we offer, but to create cutting guides. They also could be used for braces. They're allowed to have skin contact for
But
up
this
to
is
30
not
days.
like, okay, but it's not like a living organ.
We do not create living organs.
Is there that? Or is that just like cloning? Or am I asking a stupid question?
You're not asking a stupid question. So there has been a lot of talk where people want to get to the fact of creating living cells or
But
printing a heart.
You can't do that.
We are
yet.
not there today. We are starting to work with a company called CollPlant, and we are under development of being able to create breast tissues or breast implants. That,
Of course, that's what they're working on. That's where that's where the money is.
And though to some side of where a lot of people think it is, it's also a big market when it comes to breast reconstruction. So people who have gone through breast cancer
Right.
and, are in very much need to feel like themselves again, and where the silicone may not be an option, there are companies that are looking into implants that you can use that are hopefully going to be safer. And they're looking at our technology for it. I'd say that's probably the first start in being able to have some implantables within our plastics.
Yeah.
And with the hope that that is successful, I could see many more different applications to come. But for now, step one is to look into those breast implants.
I would always, looking at full implantables, bioprinting, number one is patient safety. We always have to make sure that the patient is going to be safe. And we talk about bioprinting a heart. I know there's been some, what I like to call sensationalist news stories about bioprinting hearts, lungs, etc., right? Those are very critical components to our body. And it's something that's going to have a large, I would say, regulatory hurdle to a point where
Right, because
because
the immune system is going to be like, this doesn't belong to me.
Yeah. So, we have to take into account that patient and that patient's safety, no matter what we're doing in the bioprinting or even the 3D printing space. That's of utmost importance to us as well.
Interesting. Yeah, I used to, there's this writer I know, his name is A.J. Jacobs, I don't know if you've heard of him, but he brought up the idea of one day, like, he's a vegetarian. He was saying, like, maybe one day you could go to the grocery store, and if you were a vegetarian because you didn't want to eat animals, you could just eat like an organically grown arm or leg.
Okay.
And then if you really wanted to get crazy, like, they could create body parts from various celebrities. I'm sure you guys have thought about that kind of crazy stuff too. It seems like that's your...
I would not be surprised a lot of people ask the most random things that you could create and 3D print. And I think
So
for
what?
us,
Okay, that's my question now. What are some of the most random things that you've seen done, or one of the most random things that people have asked to be done?
That I can publicly share?
Yeah.
Good question.
Oh, we can put the explicit switch on this episode if you want.
There are some really fun projects out there that are very unique and would fit into that explicit category, but there's nothing that I'd be able to publicly share that we don't have under NDA. I can talk about maybe a really fun, impactful project that we've worked on.
Please do.
There's two that I really, really enjoy, and I'll go with more the education one. And it's something that's unique to our SAF technology behind us. Is even though we're in the medical space, right, we're thinking about all our technologies holistically of how can we impact medical, education, aerospace, automotive, with all our technologies, right? And in the education space, we sponsor an organization called First Inspires, and a lot of different FIRST robotics competition teams. Last year, we donated these small vector intake wheels. They're like 2 inches in size. They're about this size. I had one in my pocket earlier, and I gave it away to a student. Otherwise, I'd be showing it to you right now. I definitely have some pictures I can share if you're looking for them. But these little vector intake wheels are these multi-axis spinning wheels. So you think of a wheel, it just spins around and around, helps with movement. Well, think of this wheel as one wheel spinning around and around, but it has multiple mini wheels on it, all at 45-degree angles. And what that does is it causes a vector translation of anything that it's trying to move around. So you put a series of those in a line, and they have those 45-degree angles all facing one direction, and you try to, I'd say take like a dodgeball, for example, and you try to move that dodgeball into a robotic apparatus, and it's actually going to translate that ball using motion that's going in a different direction than you would expect. So instead of just going in, it's actually going to move it to the side. We printed 4,000 of those last year in a week on that machine right there. Maybe not that exact machine, but the one that's in our lab out of nylon 12. And you think of economies of scale and what you can do with this technology, right? That's one example of one part, but you apply that principle to the medical industry, and you think of, well, every single individual has a unique anatomy. And you start saying, well, if I take this machine and I can print 4,000 of this one component in a week, well, let's say I print 4,000 personalized solutions in a week to a specific individual, whether it's a hearing aid, a clear aligner. There's a whole slew of other application spaces where we can use this technology, and it starts to blow your mind in what you can do.
For sure. Okay, what do you think, Allison? And what's the thing that he's holding back that he's not telling us?
As much as I'd love to share, I don't think on camera is the place to do it.
All right, well, we can all use our imagination. All right, but what's something, I don't know, fun? Obviously you've shown me some prosthetics and bones, and that's awesome. Something off the wall.
So sorry, I'm drawing a blank.
I don't know, my favorite case that we've ever done in the medical space is the one with Jenny Zabla out of Anschutz.
Jenny's
Center.
what?
Jenny Zabla. I believe she's a surgeon out there. And we worked with he's an architect by trade, Nick Jacobson, to create a anatomical model that both felt realistic, like that heart where you could squeeze it, but also looked realistic. And it was actually for a 2-year-old patient. We've got a case study on this that we can share. And this 2-year-old had a congenital heart defect, which means heart was rotated when she was born. And it's something that they needed to go in and rotate that heart back into position so that blood could pump and flow directly throughout her body. There are a lot of barriers to going in and performing this surgery. Number one is having that clinician really understand how they're going to go in without impacting that patient in any adverse ways.
Yeah.
We want to reduce that risk, reduce the risk for complications for sure, so that child is going to go on to have a happy, healthy life in the future. But we also need to make sure that their parents understand what's going on. As a parent, the worst thing that can happen to you is you have to go to a hospital to take care of your kid. And you don't know what's going on, and you want to understand what's going on, and then the surgeon or the clinician, God bless them, they show you this nice black and white picture on a TV screen or a computer screen, and
right.
that can be confusing.
And now you can actually feel them and go.
Yeah. So now we're translating those into 3D data, and then we're handing that to the patient. So either the patient or their parents can truly understand what's going on and really provide some informed consent
That's
so that they can
incredible.
go in and do that successful surgery. And that patient is happy and healthy today. So
That's awesome.
it's one really good example of the impact that I think the 3D printing industry can make on an individual and their family.
Wow. Anything else that we haven't talked about that you're just super excited about that we can't exactly do yet, but it's coming, or is that stuff top secret?
Can't do yet.
Or just what's on the horizon? What's like getting everybody extra jazzed?
Well, right now the most exciting has been our latest Origin 2 launch. So I think people have been excited to utilize the printer. It's something newer for Stratasys to get into DLP technology. And now we have a second generation, and we're excited to put it out in the market.
That's Blue Origin, like the Amazon, like Jeff
No, that's
Bezos?
our Origin 2. So sometimes people look at it's like a Star Wars spaceship or something because it's nice and red inside. But it's a direct laser projector, and so we call it DLP technology, and the chance that you can use any sort of resin, and it creates some of the nicest finish, almost looking like injection mold parts, which is different for us. When polyjet tends to be our bread and butter a lot of times in medical, it's the way to make the most colorful, the most multi-material parts that we have. Now it gives you a chance to have a little bit more strength and rigidity to some of your parts based on what type of tools maybe you're looking to prototype.
Very cool. One other, this is just one last question I always ask people in podcasts. What was something in your life that you thought was, just an example of serendipity in your life?
The serendipity almost comes back to what got me into the industry. So having worked in the medical industry, knowing that it was impacting patients, when I left, I wanted to get into sales and got into the world of 3D printing. And then now to get the chance to mix 3D printing back into healthcare, especially when we get to support our hospitals, which is direct to patient, and seeing that effect, that to me feels like the biggest serendipity moments.
That's amazing. Evan, Allison, thank you both.
It was a pleasure.
Yeah, thanks for coming by.